Let me introduce Tom Herbert, who will be presenting open source implementation of UEC's Ultra Ethernet Transport on XDP2. That's hard to say. Tom is a founder at XDP.net and traveled from Sunnyvale, California to join us today. This is Tom's first time presenting a NANOG. Welcome, Tom.
Thank you. Great to be in Texas, kind of coming from California, so it's not much of a change in terms of weather. So, a little bit about myself. I've been around a while, started my career back in the day at Sun Microsystems, and for the past, I don't know, 25 years or so, I've been working primarily in networking, specifically host networking, Linux kernel, anything to do with kind of data center networking. I spent quite a few number of years at Google, Facebook, where I actually picked up a lot of techniques and learnings about hyperscaler deployments. So it's been an interesting ride, and one of the things that I have noticed recently, there is a major shift happening. And everybody knows it. AI, excuse me, AI is completely driving everything. And what I'm seeing is it's just all across the board. It's not just networking, it's compute. They're building out data centers faster than, not as fast as they want to. Power becomes an issue. They're even building these mega racks, and the floors in the data centers become an issue. So it's a real gold rush in a sense, and of course, we need infrastructure for all of this. So today I'm going to be talking about some of the infrastructure around AI and how it kind of is changing the world. But even so, just bear in mind, all of this is still based on like history. It's an evolution from what we've done. Nowadays we know about open source. We're getting more into hardware. The lessons of the past 40 or 50 years, frankly, of the internet, they're still being applied. So it's the same thing, just dramatically newer in a sense, higher throughputs, lower latency, all of that across the board. So just bear that in mind. So the talk I'm going to give today is about a new technology, actually two new technologies, and I want to talk about XDP2 and then Ultra Ethernet, and then combining these two things. So I'll take a little bit of a poll. How many of you have heard of Ultra Ethernet Consortium? Okay. Dare I say, how many of you have heard of XDP2? Wow, that's almost as many as UEC. How many have heard of AI? Just checking if you're awake. So what's happening in the AI infrastructure world, particularly in networking? As I said, there's a lot of motivation, a lot of ambitions for very high throughput and low latency networking. And you can kind of divide the world into two major parts when it comes to AI networking. One is scale out networking, which you can kind of think of more as almost abroad across a data center network. It might be how we connect many racks of GPUs in order to do a training job. And then the other one is scale up, which is really very tightly coupled small racks where GPUs are working really in tandem trying to do a job. So as you can imagine, as things get smaller and more compressed, the requirements get more stringent in terms of higher throughput, lower latency, lower jitter. And as you move out, like in the scale out, as opposed to scale up, the requirements become a little more lax, but lax is relative here. Some of the talks today, for instance, we're talking about internet, where we're looking at millisecond latency on the real internet, and that's really good. In these data center applications for scale out, application latency is sub-millisecond, probably in microseconds, and for some of the applications in scale up, we're going all the way down to nanoseconds. So what happens is, given these new requirements, we need to revisit the protocols, the infrastructure, the interaction between hardware and software, and that's what's happening. So about, probably about 2 years ago, some people started thinking about the various problems. One of the initiatives is called Ultra Ethernet Consortium. And the idea was, let's extend Ethernet, which is kind of considered the least common denominator of the data center network. Let's consider how to apply that more to these new requirements for AI and machine learning. So we're going to start with the baseline of Ethernet, and on top of that, we're going to build a protocol called Ultra Ethernet Transport, which you can kind of think of as somewhat like TCP, but it also includes more higher level constructs like how to do RDMA, memory operations, things like that. So it's more of a complete stack, but it is explicitly designed really for AI, HPC, moving memory very quickly amongst GPUs and other domain-specific accelerators and things like that. So the group got together. It's an industry consortium. It's made of pretty much most of the industry players. Broadcom, I think, spearheaded it. Several hyperscalers are involved. So it's getting a lot of traction. And if you haven't heard of it, chances are you will. As this gets deployed, it probably will take over a lot of the data center infrastructure, like AI is doing in general anyway. So in June, they announced a 1.0 specification of the protocol. It is called Ultra Ethernet Transport. If you look it up, I will warn you, it is not for the faint of heart to read this thing. It's 576 pages. Questionable whether or not they should have split it up. I'm trying to get that discussion going. But it's a very dense specification, and we'll go into a little bit why it's so dense. It covers every single layer from layer 2 through layer 7, how to do a network layer, transport layer, how to do semantic layers where the memory operations happen. So it's going pretty well. You'll see a lot of vendors coming out. Currently, they're saying they're UEC ready. I'm not sure anyone has a full implementation with 576 pages. Probably be a while. But in parallel, what we've been doing, my company called XDP2 and a few others, we've been developing a new infrastructure, kind of a programmable infrastructure that I call XDP2, which the goal there was not so much to be protocol specific, but to look at what is the next generation of networking, especially in the data center, going to require in terms of how to deal with hardware and software in order to meet these crazy performance requirements of things like AI. And one of the conclusions we came to, and I think you might have seen the DPU talk this morning and a few others, regardless of anything, networking in the future, especially when we talk about host networking or even switches, it's going to have super high performance. That's one requirement. And again, performance goes, it's a spectrum, high throughput, up to multi-terabits in some cases, super low latency, like I said, that can get down into nanoseconds, and low jitter, low variance, all of that good stuff. But on the other hand, it has to be flexible and malleable. We can't be in situations anymore where a company has to swap out $100 million of hardware just because they found a new bug or they need a new feature. So that basically means we need hardware devices that are programmable, which basically means we want to have software that we can write that figures out how to run at the speed of hardware. XDP2 is kind of the design of that, and I'll get a little bit into that in a bit. So when you think about these two things, especially the complexity of Ultra Ethernet, its requirements, and how it's going to have to adapt to even unknown applications in the future, combining that with a programming model like XDP2, which allows an implementation to be written that can then be ran on all this disparate hardware most efficiently, that seems like a good match. So that's kind of the 3 parts we're going to cover today. So XDP2, I call it a programming model for the data path. Data path you can think of as how packets are processed. That's the obvious one. But we are getting more into not just packet processing, but this is really protocol processing, like terminating. You can think of terminating TCP. That's kind of the equivalent. All the work to do that. So it's really a lot more complex than, say, a firewall or a NAT device. It's really doing protocol termination, which means it's going to have state and timers and a whole bunch of other stuff that you might normally not need in plain packet processing. So the goal is user writes their data path in a language that's convenient to them. So it's going to be language agnostic. That's going to be critical. Their code compiles to a wide variety of targets, and I'll get in a bit into that in a moment. And we can think of this as maybe a convergence layer for P4, eBPF, and DPDK. So a little bit of a regression. Those 3, P4, XDP, eBPF, and DPDK, VPP, I think there's actually a talk on VPP next. Those 3, though, are kind of like the first instances of programmable data paths. They're a little bit different. So P4 you may have heard of. That's explicitly for programming high-performance hardware in a programmable way. So it's both a language and a runtime environment. XDP, eBPF. eBPF is huge right now in the Linux community. That's kind of how we're really writing kernels anymore. It's kernel code. We're trying to get out of writing kernel code and use eBPF, which is more like user space code that we can insert it in the kernel. So people love it for its flexibility. And then DPDK is kind of like that, but in user space. DPDK, you might be familiar with. It's pretty popular in the telco brain. So we're thinking this of XDP kind of as a XDP2 as kind of a convergence layer for all of that. So I'll give a little bit of background on XDP2. There is a little bit of a theory and some goals behind that, what I call the 5 pillars of that high performance. And the pillars are parsing, lookup tables, accelerators, flow logic, and parallelism. So these are really the 5 kind of computer science-y things, for lack of a better term, that you really want to have in a high performance data path. So, parallelism, it's well known. We've seen that in a talk earlier about SSH improvements. Get things to run in parallel, that can help performance. Some of these others are kind of networking specific. So parsing is a very particular problem in networking. When you receive a packet, we have to split it up into little bits and pieces. This is one of the hardest problems because it can't be easily handled by hardware. It kind of has to be done in a serialized fashion, and that's where people have gotten into trouble, especially on the internet. Some of you are probably familiar with the saga of IPv6 and extension headers and how difficult extension headers are to do. The other ones are similar, lookup tables. We're always going to need lookup tables. Accelerators are what they are. I mean, they're hardware accelerators to make certain operations go faster. And then there's all that flow logic, and the flow logic really has to do with how are we going to implement these protocols and the protocol logic. So these pillars are going to support flexible and high performance communications infrastructure. And the foundation of all of this is the programming model, but also domain specific architecture. So from now on, or a trend I should say, in the industry is we're going to start building more and more solutions based on domain-specific architecture, meaning we're going to build the solution around the problem, and that gets us past some things like Moore's Law. GPUs are definitely the poster child of that, so I think networking is going to see more and more of this. So the model of XDP, I call it write once, run anywhere, run well. That's kind of a play on the old Java mantra. So on the left side of this picture, like I said, we want the user to write their program in whatever language they want. So we're not going to force a programming language. We compile that into an intermediate representation, and then a backend compiler takes that intermediate representation and turns that into optimized bits for the back end. So what's important to me here is make this as easy as possible for the front end user, and we're going to do the heavy lifting, so to speak, to translate that into the back end hardware. And this is really where the flexibility and the performance comes through. So we need this kind of this whole solution. It is ambitious, but we think the technology is there, especially in the compilers, to pull this off. So XDP itself, XDP2, has several development vectors, and we are working across the board on these. I mentioned compilers, the applications, so the UET that I'll talk about in a moment, that's one of them. There's also Linux kernel component here that will help a lot, so some of the kernel problems we can actually solve in this model. Hardware acceleration, as I said, the further we go, the more hardware we're going to need in the integrated data path. And this is something that's actually new for me. 10 years ago, I would have said, no, software, we just need software. Just give me good hardware, good NIC, nothing special about it. I'll write the software to make it go fast. I think we've hit a turning point. Now, software data stacks cannot keep up. We actually have to integrate hardware. But as I said, the challenge is how do you make that integration seamless and programmable and flexible? So it's a nice challenge. We are supporting, so far, the model in C. We've done a little bit of P4 work, but we do intend other languages. Like I said, it really is something where we want to make this easy as possible on the user. Let's talk a little bit about Ultra Ethernet transport. So like I said, the Ultra Ethernet Consortium, they are developing what they call a full communication stack architecture to meet the so-called growing demands of HPC, high performance computing at scale. So they're going straight to full hyperscaler data centers, big training jobs that take thousands of machines, exchanging terabytes of data really quickly. That's the target. Like I said, it is more of a scale out, so it's a little higher than within a single system, which would be more scale up. So their sweet spot is going for the big data center, large, up to like 1 million connections, 1 million hosts connected. The Ultra Ethernet transport layer then is a major part of this. It's kind of consumes the protocol delivery layer that provides reliable protocol delivery. You can think of that as kind of like TCP. And then the messaging semantics for upper layer protocols, more the transaction, or what they call the semantic layer. UET has several features. It's designed for low latency, high throughput, simple implementation hardware and software. The way to get that, like I said, we can always go back and look at TCP, what worked, what didn't. So we know, for instance, that one of the most critical things in a protocol like this, especially for scale out, is how you deal with congestion in the network. How do you detect it? How do you fall back? How do you route around problems? So all of that has a lot to do with low latency. Some of these jobs, we really need super high reliability. If you're running a training job and you have inconsistent reliability and you're dropping packets, that can actually increase the length of time an hour training job runs to like 1.5 hours. People get really unhappy. That's dollars being blown. So we really want to make very highly reliable, high throughput implementation. Now the simple implementation, that's obviously subjective, depending on how you look at it, but it is a requirement. So one of the things, like I mentioned, is hardware has to be part of the solution. So they are thinking about how to do that. There's some interesting kind of innovations. One of the interesting things is lightweight connections. So if you look at something like TCP, it has a very formalized connection process, expect long-lived connections. What they did in UET, lightweight connections, they can create connections on the fly. The value of this is less memory needed for long-lived connections. And if you orchestrate things right, the lightweight connections really have very little overhead. So it's pretty exciting stuff. Everything's message, initiator, target-based communication. So that goes back kind of like the iSCSI or storage world. So initiator makes a request, say for memory or to write a memory block of memory, and the target will do that and reply with a response. I mentioned the congestion control and rapid response. One of the big differences, though, between TCP and not just UET, but pretty much all of the emergent protocols in this space, they will support both unordered operations and ordered. Unordered is really critical because if your packets are arriving out of order, you're dropping stuff, we still want the ability to act on them, at least do data placement. So that's a first-class citizen. Like I said, it'll be true for this protocol, but probably most protocols going forward. Multipath and packet spraying, this is a really critical one. So for those of you who are running data center networks, you're probably looking more and more into packet spraying techniques. This means that instead of, say, a single connection or a single flow following a single path through the network, like the old days, nowadays people are starting to spray those across all paths. So even for a single connection. And the reason to do that is it guarantees uniform load distribution across all of the network paths, which is good. Obviously, though, at the receiver, now we have problems of getting packets out of order, so we have to have protocols that are tolerant to that. TCP is kind of okay with that, but these newer protocols, they're kind of making that a first-class citizen, so they will have better semantics to handle out-of-order packets. On top of everything, we do want to implement RDMA, collective operations. Those are straight out of kind of the AI world. But also this will be applied for other HPC type applications. One thing I would mention is UET in particular will be run over UDP. This is also something for the data center operators out there. You should expect almost all new protocols are going to be over UDP unless somebody figures out how to run the protocols without even IP and run them straight over Ethernet. UET doesn't do that, but some others do. So the reason that UDP is so useful is it's kind of the standard, a way to make it standard. And it really comes down to some of the switches. They work best with UDP or TCP. TCP is a done thing. That's its own transport layer. So what we do is we take UDP, we encapsulate a whole protocol in UDP. So Quick's kind of started this, but it's going to be true for UET and other protocols. We encapsulate all that in UDP. And then when the switches see this, they see a UDP packet instead of a Quick packet or UET packet. So they know how to handle it. In particular, they know how to do ECMP routing by looking at the UDP ports, taking the hash and routing it on multipath. And it also has to play with how we can do packet spraying, because in packet spraying, what we're going to be doing is we're going to be setting the UDP source port as entropy, and then the switches, when they route it, they don't have to know that this is packet spraying or even that's from the same connection. All they do is route it based on the UDP ports, which says this port's different, so we can take a different path, and that's how we're going to accomplish the packet spraying. So we don't even need any knowledge in the switch, really for UET, although there are reasons to do it for other reasons, but UET is completely deployable as is in a data center just using standard switch mechanism. That's a key thing. So I'll go over a couple of the layers real quickly. Packet delivery sublayer, like I said, this is very TCP-like. It implements reliable in-order or out-of-order delivery, but it is reliable. So if packets are dropped or dropped for congestion or dropped for some other reason, they will be retransmitted in the right mode. There's a few modes of UET, it turns out. Most of them are reliable, so they'll retransmit if packets are lost. So we have normal ACKs and NACKs, packet sequence numbers. TCP is a little bit different. It has a byte sequence number, so most new protocols are going with packet sequence number, a little better for scaling. And then if you look on the picture, there's a SPDCID and a DPCID. These are kind of the connection endpoints. They're like port numbers in TCP. So they serve basically the same purpose, but they are detached from the UDP port numbers, which is kind of nice. So the protocol is self-contained, doesn't rely on any of the UDP fields. It only relies really on the IP addresses for proper delivery. The layer above that, which is called the semantic sublayer, this is where they've defined the various operations. So the normal RDMA operations, send, write, read. Send is sending a kind of anonymous buffer to appear. Write is write an explicit memory location. Read is reading from an explicit memory location. They also support atomics, which is kind of interesting. So we can atomic increment, atomic sets and things like that across a network. The goal here, you can think of this as trying to make it look like remote memory. So if an operation works in remote memory, it makes sense to do that as atomics. And then they support some other little higher layer concepts to try to synchronize the sender and the receiver of data. But the thing is, this actually does result in a fairly complex header, as you can see. So the standard header is 40 bytes. There's actually some variants of this. Some are actually larger, like for the atomics. There's what we call an atomic extension header. Some are smaller, so sometimes we can optimize those out. One of the things that you'll notice, and again, this is kind of why it's 576 pages, it's very clear that there were a lot of ideas coming into the consortium, and they wanted a lot of different variants. So there's basically 3 fundamental packet sizes, and then 16 different operations. And on top of that, there's a couple of other different variants, and then there's connection management and things like that. When you start to add all that up, yeah, it kind of looks like a bit complex of a protocol. And that also means that I don't think it's possible for anybody to implement this whole protocol in hardware. So we'll definitely need a software layer to do a lot of the work. Okay, so XDP2, programming model for the data path. It's a common way to program hardware, various forms of hardware, including higher layer protocol constructs. There's UET from UEC. It's a nice, nifty new transport protocol for RDMA-like constructs for AI and machine learning. Obviously, to me at least, we want to put these together. So I'm going to call this implementing UET in XDP2. This is completely unreadable. Don't worry about that, but that red box is the middle layer, which is really where the interesting stuff is to implement. And this is primarily the packet delivery sublayer, which is that TCP-like layer, and it's the semantic sublayer, which is the send, read, write command primitive sublayer. Outside of that, on the left side is libfabric. That's API that they've chosen. So that goes all the way up to user space. That's the interface, programmable interface. On the right, we have a security layer. So they definitely want to integrate security as an option, but it is a first-class citizen in the protocol. And then they have an Ethernet port. Ethernet starts fairly simply, but they are doing some interesting things. Link layer retry, some more priority flow control. There's a credit-based scheme, credit-based flow control management. And that's pretty neat stuff. But it is kind of separate out, so it is nicely layered. So the red box is really where we're going to focus our efforts with the XDP2 effort. So if we divide it up into the various components, it's pretty clean. This is just doing network processing. So we only have a few sources of input into this system. One is the receive path. So when we receive packets destined for some UDP port number, that's going to be a UET packet. And then we go into processing the UET packet. Like I said, that's where parsing takes effect. So we have to parse the first layer, which is the packet delivery sublayer, process that, If that's a good packet and it's reassembled, it goes to the session semantics layer. That's the second layer. That processes what the request, and then if that's good, it can be sent up to the lib fabric or to the backend memory system to fulfill the request. So there's kind of an upper layer processing that happens there. Transmit path, just kind of the opposite, obviously. Whenever we need to send anything, it's going out. So if we send data to a remote system, it takes a reverse path. It goes through the API, through the ULP into the session semantics layer. That gets its own header, and then given that header, it's sent into the packet delivery sublayer that can actually packetize things, so it could break up a big message into small parts, and then that sends it through the Ethernet. There's various layers here of queuing. There's also priority queuing and things like that, at least in the Ethernet layer. All of this is controlled by a type of connection, like I mentioned, what we call packet delivery context, like a TCP context, and that's set up by the lightweight connections. So those are the two primary sources of input. Timeouts are super critical. So if we drop a packet, the system will detect it through the packet delivery sublayer, see that the packet's dropped, and can deliver it again. If it didn't get an ACK, it would deliver it again. There's also another layer, and this is kind of a nice thing that I think you're also going to see in protocols like this. The congestion management is treated as a module outside of this. So what the congestion manager does is it takes all of the inputs, the round trip time, variance, and all of that, takes all those inputs, and it can produce congestion parameters like the congestion window to send. And it's pluggable because we can swap out different forms of congestion management. And that is actually one of the nice areas of research. So how we do congestion management, the algorithms, can affect throughput widely. Obviously, the better the congestion management, the higher the throughput, good put at least. But also we have to meter that against, what's the application, what's the network. So it has to be very adaptive. So this is really the sort of thing you do want to have be kind of pluggable. And now in the picture, it does show kind of the two paths. There is a connection between the receive path and the send path because we have to do ACKs. So just like TCP, we need to send ACKs when we transmit. So the XDP2 services that are needed for this, like I said, XDP2 is really geared not just for packet processing, but for protocol processing, which means there's going to be extra constructs, especially when we start getting into stateful protocols. So protocol parser, this is something in XDP2 that's actually its own thing for various reasons. Way we even code up a parser and design it has a lot of impact on how efficient we can make it. We basically want a parser to be more in declarative representation than imperative. So the standard way we used to do that in C really doesn't cut anymore. Tables are critical. Tables are as simple as, here's a key, give me output, to as complex as, here's a bunch of bytes, do a TCAM look on this, give me an output. And of course, everybody's familiar with route lookups, longest prefix match. So there's various forms of tables. Which ones are needed in this particular path? Probably more the simpler ones like the CAMs. Definitely needed for protocol parsing. Timers, as I mentioned, these are needed for packet retransmissions. Timers are unpleasant for one reason. Imagine you're on a network that's never dropping a packet. You may never see a timer expire, but the problem is we still have to keep setting them and unsetting them. It's really annoying. So one of our one of the things we're focused on is how to make timers really super efficient. How do you reset a timer quickly? That's not the easiest problem in the world. So there actually is some interesting things we're doing there. One of the other areas that is kind of emerging, how do we even structure the data and communicate the data between various components? So we definitely need scatter gather lists, we know that. But is that the best way to do it? In Linux, we have SK bus, if you know FreeBSD, you have M bus. So it always seems like we need some data structure to kind of hold the data and represent it. But the problem is when you start talking about hardware and software and trying to kind of meld them, how do we get hardware to understand something like SK bus or M bus? So what we're actually doing is we're designing a data structure kind of made for hardware. It's a lot simpler than anything in an operating system. And we're hoping that that actually has merit to use in hardware. One of the more interesting things are bitmaps. These are surprisingly becoming quite prevalent, especially for conveying like what packets have been received and what haven't. So we can design a bitmap of that. And some of these bitmaps, UET uses like 64 bits, but some of the other protocols that are similar, they're using 128-bit bitmaps or more. These are kind of long. And if you've ever looked at bitmaps, the concept is simple. You just have an array of bits. And if you set a bit or unset a bit, it's a little flag in itself that's idempotent from the others. So it indicates a binary state. But now we want to extend that to use a whole bunch of processing and even shifting a bitmap because we want to shift left by 10 because those packets have been acknowledged, and now we want to shift the acknowledgement bitmap. That's kind of a difficult problem. So there's actually new hardware techniques just to deal with bitmaps. This is something that we didn't really see in TCP. A couple of other things. Dumping UET packets is going to be kind of important. I think there's already some work on that for Wireshark. Configuration facility, as you can imagine, a system like this is going to have a lot of configuration. And for XDP2 in particular, we definitely want a CLI in order to be able to control this in real time. Just to give you an idea of kind of the complexity of this, this is what I call the parse graph for UET. It has those two main areas. So the kind of the yellow nodes are the packet delivery sublayer. But if you look at that, there's actually, what do we have, 5, maybe 6 different classes. And each class has 4 different packet types. And then we go to the semantic sublayer, it's kind of the same thing. You have different classes with many different packet types. So this is not simple. It's actually more complex in TCP. So it's one thing to consider, especially when we get into something like parsing, how do you efficiently deal with that level of complexity? And all of this is just part of the stack on the left, which is more the whole stack. So where are we? So this project, it's pretty new still. And what we're doing is we're developing this as an open source model. My goal is to make a reference implementation of UET, fully open source. We'll be in C to begin with, but like I said, other languages are welcome to join. Currently, we've done all of the infrastructure work for it. Those packet formats, which I consider kind of the first level of implementing a new protocol, those are completely done. It reveals a lot, by the way, when you have to actually write out what a packet format looks like in C, especially if you're on a little Indian machine, you start to see patterns and, oh, I wish they would have did this instead of this. So there's some feedback you can give. So even the packet format has a lot to do with how efficient it's going to be. There's some library functions that are dealing with UET. We'll actually be pushing a lot more to actually deal with the protocol in a bit. We have some tests, if you look at it. Right now, we can test sending all the different packet types and receiving them, which again is very enlightening. One of the nice things is, and a source tool packets, UET, we have a couple of Python scripts that can actually generate various UET packet formats. It's quite useful. And then there's some pretty good documentation. So it's still work in progress, and like I said, I do intend to make this first in implementation so we can show basic connectivity, connection management, things like that. And then we'll probably have a real use case. It would be cool if we could put this into Linux, for instance, as an eBPF hook maybe be the back end of RDMA or something like that. So yeah, there's quite a bit of development to happen there. Anyway, if you're interested, that's the GitHub xdp2-dev/xdp2. And that's all I have for today.